Alright, chemistry students, welcome back. Filming another video. This time the topic is reaction energy. So, we've discussed a lot about chemical reactions this year, but we haven't really discussed the energy associated with the reaction. We have so far been able to draw equations and say if we combine this chemical with this chemical, we'll get this result. But that has one fatal flaw in that it ignores the energy involved in the process. We know if we take nitrogen and hydrogen and just jam them together, we don't necessarily get a reaction to form ammonia. Why is that? And the answer is that there are energy barriers involved in the formation of chemical bonds. And so what I'm going to explore today is how energy in chemical bonds works, what is the energy in chemical bonds, and where does it come from? So the first term we're going to talk about is this delta H that we have brought up briefly when we were talking about chemical equilibrium. And this delta H value is known as enthalpy. And very, very generally, we can summarize it as the energy involved in the reaction. So we know that because we've talked about delta H in the terms of exothermic versus endothermic reactions. Exothermic reactions have a negative delta H, whereas endothermic reactions have a positive delta H. That shows where the energy is going. If it's exothermic, the energy goes out. If it's endothermic, the energy is going in. So what is the difference between an exothermic and an endothermic reaction? How can certain reactions release energy where others take in energy? And where does that energy come from? Where does it go? That's the topic that we're going to hope to answer today. So the important note here, and this is very important because it's probably backwards of the way you're thinking of it from your previous knowledge of biology. We need to start thinking that energy is released when bonds are formed. And it takes energy to break a chemical bond. The molecules of our body are bonded together right now. They're not falling apart. They don't need an input of energy in order to stay together. It takes energy to break a bond apart. We have to put energy in to break a bond. And when you take unstable molecules and form them together, that ends up releasing energy because you go from an area of high potential energy to an area of low potential energy. This is sort of opposite of the way you've been taught in the past, in that if you took biology last year, you probably looked at ATP and said, well, the energy is stored in the bond, so when you break ATP, you create energy. Well, that's not necessarily the case. What's actually happening is when you break ATP, the high energy phosphate bond is going to bond with water, which is a more energetic bond, so you get an energy gain from that chemical reaction. The physical breaking of the ATP doesn't actually release energy. You're just moving energy from one place to another through a chemical reaction. So this is the big point that you need to get through. When you form a bond, you release energy. It creates a release of energy. And when you break a bond, you have to put energy in order to do that. In order to make this a little bit easier, think of it like this. When you have two hydrogens by themselves, those hydrogens have one valence electron in their outer shell. That valence electron is unstable. We know that all atoms are seeking to form an octet. With hydrogen specifically, it's looking to fill its outer shell with two valence electrons, and it will accomplish that by bonding. But when it's in the unbonded state, that one electron is kind of jittering around like crazy, trying to find a partner. And it's an extremely high energy interaction. So this valence electron is zipping around like crazy until it finds a partner to pair. Once these pair, the two electrons that are moving around like crazy join together, and then they kind of relax. It's kind of like if you start at the top of an energy hill, you have a lot of potential energy. And then once you form a bond, that potential energy is released in the form of heat. Typically, if we think of this as a hillside, if there were rocks on the top of this hillside and they were to fall down the hill, that their potential energy that they had when they were at the top of the hill would be released in the form of physical damage to the hill, in terms of sound, in terms of heat energy. And that's the same thing that happens when you take an unstable system, which is two unbonded atoms, and then bond them together. Once they bond together, that high energy state relaxes and the extra energy that was there before gets released to the outside as heat. Once it's here, it's stable. It requires energy to push it back up the hill to give it more potential energy. In order to break this bond apart, we have to put energy in. That's the main concept that I want you to get from that. So, one of the ways that we look at this in chemistry is through what's called a reaction energy diagram. In a reaction energy diagram, we graph enthalpy, or the energy of the reaction, on the y-axis, and we graph the progress of the reaction down here. So we start with our reactants, and our reactants have a certain amount of energy associated with them in their bonds. So what happens is, as we start a reaction, we will progress from reactants to products which will have a different energy. And the difference in the bond energy of the reactants and the products is what's known as our delta H value. That tells us whether a reaction is exothermic or endothermic. So a way to think about it is, if our products have less overall energy than our reactants, then that extra energy, that gap in energy, needs to go somewhere. If we have more energy in our reactants than our products, then that extra energy goes out. So this process would have a negative delta H. You see there's a drop in delta H. And this specific process would be an exothermic reaction because it would have a negative delta H value. We could also have a reaction energy diagram in which our products are more energetic than our reactants, where if we were to have an exothermic reaction, we could have something like this dotted line I'm drawing, where the products would be up here. That would be an endothermic reaction because you would have to input energy in order to go from reactants to products, because the products have more overall energy than the reactants. Now, another concept here is that anytime we go from reactants to products, we have to break all of the bonds that are in the reactants. If, for example, we take our reaction where we go from nitrogen plus hydrogen to ammonia, we have to break all the bonds with nitrogen and all the bonds with hydrogen and then reform them. So anytime we break bonds, we have to push this up the potential energy hill. We have to provide energy in order to break those bonds. So this is why you can't just combine chemicals and have them naturally react with one another. You usually need to have some spark or some input of energy in order to have that work. And so on this reaction energy diagram, we see this in the terms of this hump here between reactants and products. Once we start our reaction, we have to overcome this energy barrier in order to get to products. Even though our products have less energy than our reactants, we still have to go up in energy before we go down. This state at the top here is where all the bonds have been broken. It's at the highest part of this potential energy hill. So this energy that's required in order to cause the reaction to go forward is what's known as EA, or activation energy. We have to provide the activation energy to the reaction in order for the reaction to occur. So when you see a reaction energy diagram, you have this hump right here, and this amount of energy, this EA, is the activation energy. It's how much energy you need to supply in order for the reaction to go forward. So from this, again, we can summarize the distance between the bottom of the graph and the reactants is how much energy the reactants have, the enthalpy of the reactants. The gap between the bottom and the products is the energy of the products. The difference between them is the delta H, and then the amount of energy that you need to supply to overcome this extra energy barrier is the EA, or the activation energy. Now, you'll notice that I drew this blue line here, this blue dotted line, to show something that I needed to show in terms of catalysts. So we talked catalysts when we did equilibrium, but the only thing we said about them is that they don't affect equilibrium. But we know that they do something because they speed up a reaction. Well, the way that a catalyst acts is that it actually lowers this activation energy barrier. If we add a catalyst, it makes it easier on the atoms to be unbonded for a brief period of time. It might grab onto the unbonded atoms and then bring them together and then let them go, and then grab another pair and bring them together and let them go, in order to make it easier or more stable to be in this unbonded state. And that has the effect of lowering this activation energy barrier that's required to go from reactants to products. It makes it easier to go from reactants to products. And as we saw in our equilibrium unit, what that has the effect of doing is it speeds up the reaction, but it also lowers the activation energy barrier between going from products back to reactants by the same amount. So the end result is you have no effect on equilibrium, because it's easier to form products because we lowered the activation energy barrier, but it's also easier to form reactants because of the same reason. So the end point is that catalysts act by lowering the activation energy barrier. Okay, I wanted to cover bond enthalpy, but I'll shoot that in another short video because this video is running a little bit longer than I expected. I hope that clarifies some things. Again, remember, bonds forming is an exothermic process. Bonds forming releases energy. Bonds breaking requires us to put energy in to break those bonds, to push it into a state where it's not stable. I hope that helps. Let me know if you have any questions in the comments, and I will see you in class.